friends, Miss Manu here.
And also Miss Tyler.
And we are going to do the intro to gases notes, so make sure you get out your notes template, because we're going to have fun today.
Pay attention and write stuff down like I know you don't do at your house.
Yeah. Next. Alright, so about gases. Gases respond in really predictable ways, as we're going to demonstrate here, and then you'll see later on this week during our simulation. Basically, when you change pressure, temperature, and volume, and the number of particles, it affects other things.
Yes, correct. Also, so, for a fixed amount of any gas, if you change one variable, i.e. pressure, temperature, volume, that is going to affect all of the other ones.
So we have four main gas laws that we're going to focus on this unit. One is Boyle's law, the next is Charles' law, the third is Gay-Lussac's law, and the fourth, the ideal gas law, we'll cover next week.
We don't need to deal with this yet. It's my favorite one, but we don't need to deal with it yet.
Alright, so we're going to demonstrate Boyle's law.
Yeah. With a marshmallow in a syringe, because who hasn't looked at a marshmallow and said to themselves, you know what would happen if I put it in a syringe? Not me, so let's do it. So, let's think about this for a second. We have a marshmallow which is flexible. We've all smushed one before. So if we decrease the pressure on the marshmallow by drawing back the syringe, you can see how it grows, right? It gets slightly bigger. The easier one to see, though, is when you increase the pressure and make it get real little and wrinkly and ugly. Decrease, it grows. Increase pressure, it shrinks. This demonstrates the relationship between volume and pressure. Even though obviously a marshmallow is in a gaseous substance, you can see how that works. Look at this formula. It looks exactly like M1V1 equals M2V2 because you were going to use it the exact same way, except instead of molarities, we've got pressure. This is the mathematical relationship between pressure and volume, which you just observed here.
All right, Charles' law, we're going to demonstrate over here. It's not quite ready yet. All right, friends, I am here to demonstrate Charles' law. So what I have here is a soda can with some boiling water on the inside. I have about yay much. It's boiling for the last few minutes.
Yay much is a scientific term, FYI.
Yep. I don't know, 50 milliliters? Didn't measure. Here I have a bucket of cold ice water. So what I'm going to do is I'm going to dump the hot can into the cool water, cooling down the air that's inside the can, and you're going to figure out what happens. It's always so scary.
Wow.
So here we can see, I don't want to touch it, it's probably really hot. We had a hot temperature, or the gas particles inside that can are really hot, bouncing around. When I submerged it into the cold water, it cooled down that temperature of the air particles. And then what happened to the pressure? Oh no, shoot.
Volume.
Volume! What happened to the volume? Pressure's the next one. So this is Charles' law. We have V1 over T1 equals V2 over T2, where V is volume and T is temperature.
All right, next we have Gay-Lussac's law, which is going to be demonstrated by the egg in a bottle, or in this case, actually not a bottle, an Erlenmeyer flask instead. But basically what we're going to do is we're going to take this egg, right, and we're going to strike a match and we're going to put it in there, and the match is going to obviously, hopefully, burn the paper towels like it's supposed to, and then you put the egg on top, and then stuff happens, hopefully. So, we'll see.
As we can see right now, the egg is perfectly seated on top of the lid of the Erlenmeyer flask. Not going in, even if I give it a little shove.
Oh, it went out. That's depressing.
Just
Hold on, I gotta do it again. Okay, hold on. What if we do it like this? Okay, put it.
so much longer. Look at it go!
Why is it so slow?
Because you didn't let it burn enough.
You didn't let it burn enough. But it did the thing like it was supposed to do.
Boom!
That happened.
Go.
Right, so the egg did the thing, right, even if it was slow. But the reason that that's important is because of this fun mathematical relationship that looks pretty much exactly like the last mathematical relationship that Mannering was talking about, except instead of volume, this time we're dealing with pressure. Pressure over temperature equals pressure over temperature. So we still have P1, T1, P2, T2. So we still see a similar thing to that dilution formula, it's just divided instead of multiplied. So hopefully if I give you a problem that involves this, you'll be able to like mathematically solve it. But if not, we can help you. Next.
So a couple of things to remember about these formulas, equations, is that we have to be within certain units for them to work. So for temperature, all our formulas that involve the T, we need to be in Kelvin. Do we remember how to convert from degrees Celsius to Kelvin?
Hopefully, but if not, you're gonna need to take your degrees Celsius and then add 273. Yes, it's that easy. Hopefully you can remember that.
Now for volume, we always want it to be in liters. Do we remember how to convert from milliliters to liters?
Hopefully, but if not, once again, it's pretty easy. All you're gonna do is you're gonna take your milliliters and then find that decimal place, and you're gonna move that decimal place 3 spaces to the left, and then you're gonna fill in any zeros for any blank spots, and then you got liters. Congrats.
Or just divide by 1,000.
That works
Same.
too.
All right. And we have a new unit we haven't talked about yet, and that is pressure. So we have 4 different possibilities that we can use for pressure, because you know, 1's kind of lame, 2's too easy. Might as well make it 4.
Also, there's more than that, but we're gonna use these 4.
Truth, there's like 7.
No.
So the first one is atmospheres. We abbreviate that ATM.
Then after that, we got kilopascals, otherwise abbreviated as KPA.
We have millimeters of mercury, or mmHg.
And finally, PSI, which we didn't add what that actually stands for.
Which is pounds per square inch.
That's what you use when you fill your tires up, right?
Yes.
Yeah.
Mrs. John's on a roll.
Okay, so we have some nice equalities, conversion factors, fun stuff for converting between these 4. Because, hey, guess what? We're going to ask you to convert between these 4 and also possibly other things as well, but mostly these 4. So we have 1 atmosphere equals 760 millimeters of mercury equals 14.7 psi equals 101.3 kilopascals. What that means to you is that if you have atmospheres and you want kilopascals, this is the same thing as that. So you can use that as a conversion factor in your T-charts to do that. If you had millimeters of mercury and you wanted PSI, here's your conversion factor. You do not need to use all 4 every single time. This is just saying, hey, this equals this equals this equals this, so you can convert between all of them. Also, there's this one 1 inch equals 25.4 millimeters, just in case we give that to you.
Yeah, because we might get a little crazy. Instead of giving you millimeters of mercury, we might go, ooh, inches of mercury, and then you'll have to do a 2-stepper. All right, so we have an example problem for you just so you can practice setting up those pressure conversions. We want to know how many atmospheres are in 34.6 psi.
And you'll notice that this doesn't look exactly like the little train tracks or T-charts that we've been using, but it's the same thing, because if you just kind of go like this and imagine a T-chart, it's the same thing. So your given number is going to go in your upper left. How do we know this is the given number? Because the problem gives it to you over your placeholder 1. Then we use our conversion factor, which we could find because of that last slide when I said this equals that equals that equals that. 1 atmosphere is the same thing as 14.7 psi. And lo and behold, we do that multiplication and that division, we get 2.35 atmospheres. If that was too fast for you, please ask us about it in class.
We got office hours, we got ELT, we got
Other
in
stuff,
class.
I don't know.
fun.
Next.
Alright, so here's another example. I want to know how many kilopascals are in 3.1 atmospheres. So once again, I start with my given in my top left box. I'm going to take that unit and slap it down in the bottom right of my T-chart, or train tracks as I call it. Where we want to go goes up top. And once again, like Ms. Seiler said, we just refer back to those equalities. And I know that 1 atmosphere is the same as 101.3 kilopascals. Multiply across the top, divide by the bottom, and I get 310 kilopascals.
Why is the 310 not the exact number that comes out the calculator? Because sig figs.
Figs.
They never go away. All right, now, you, my friends, colleagues, students, individuals, you are going to try these 3 on your own. On your own, all by your
Oh,
own
I
self.
zoomed in too much.
No.
All right, so pause your video, try those answers now. All right, so these are our answers. For number 1, you should have gotten 1,605 millimeters of mercury. For number 2, you should have got 1.97 atmospheres. And number 3, 132 kilopascals.
If you didn't get that, please ask us about it.
Come
and we're
see
happy
us.
to show you how we got that. Because hopefully at this point, since we've been doing conversions, literally since the beginning of the school year, you're somewhat familiar with how this works. But if you're not, that's what office hours and ELT are for.
Whoop, whoop.
Cool.
All right, so now what happens if your given number is in inches of mercury and we ask you to convert it into another type of pressure? That's our two-stepper.
So this is going to kind of mirror what the two-steppers for stoichiometry look like, except it's not stoichiometry, it's just a two-step conversion. So you should have that two-step T-chart that we use, except you're going to fill in some different numbers. However, comma, the given number still goes in the upper left, just like it always did. The placeholder 1 still goes in the bottom left, just like it always did. Then we have a conversion factor and another conversion factor. So, we're starting in inches of mercury. That's not one of those 4 equalities that we need. However, we did tell you how to convert between inches and millimeters. So, to get out of inches and into millimeters, you use that 1 inch equals 25.4 millimeters conversion situation to get into millimeters of mercury. That's what this step is doing for you. Then, after you are in millimeters of mercury, you're going to use the equalities to convert between millimeters of mercury to atmospheres. So that's why you can stack those right next to each other. Multiply, multiply, multiply. That's going to give you a number on the top. Multiply, multiply. That's going to give you a number on the bottom. Divide and solve.
Are you done?
I don't know.
Yeah, I think so.
Yeah,
So,
we're done.
if you have any questions, come see us, ELT, office hours, during class. You can come to either one of us. We are here to help you.
It's true.
Like that little